Hey, everybody, and welcome to 8-3, Testing a Claim About a Mean. Testing claims about a population mean with sigma not known. And the objective is to use a formal hypothesis test to test a claim about a population mean mu. And then we have the same notation. N is the sample size, X bar is the sample mean, S is the sample standard deviation, and mu sub X bar is the population mean, which is the mean of the sample means. Testing claims about a population mean with the sigma not known. We have some requirements. The sample is a simple random sample, and either we know the population is normally distributed or N is greater than 30. Then we talk about test statistics for testing a claim about a mean. We're going to find p-values in StatCrunch. The degrees of freedom is the sample size minus 1. This is from our textbook, and this is what basically it would look like. Here on the left is degrees of freedom. And then it depends on if we have a one tail or a two tail. And we'll talk about that a little more. And then these are going to be your areas. Since we have StatCrunch, we can find our p-values and our critical values using StatCrunch. We have an example. An author obtained times of sleep for randomly selected adult subjects included in the National Health and Nutrition Examination Study. And those times and hours are listed below. Here are the unrounded statistics for this sample, N equals 12. We have X bar, S, that's our sample mean and our sample standard deviation. A common recommendation is that adults should sleep between 7 and 9 hours each night. Use the p-value method with a 0.05 significance level to test the claim that the mean amount of sleep for adults is less than 7 hours. First, do we meet the requirements? What were the requirements? One of them is that it has to be from a random sample, randomly selected adults. We have to have either N is greater than 30, I only have a sample of 12, or it's from a normally distributed population. The other requirement is going to come from the data. I already inputted the data here, and I'm going to go to graph, QQ plot, select var, add this correlation statistic, compute. And this correlation number, the closer it gets to 1, the better my correlation is with a normally distributed population. Because it's 0.962, we're going to make the assumption that this is a normal curve. I have the requirements are met. The next thing we want to do is find the claim. To test the claim that the mean amount of sleep for adults is less than 7 hours. We have a null hypothesis, H sub 0, and H sub 0 always has equals. We want to test the claim that the mean amount of sleep for adults is less than 7 hours. For the null hypothesis, it equals 7. The null hypothesis always has to have an equal. And then H1, which is my alternate hypothesis, mu is less than 7 hours, because that's the claim. We found the null hypothesis and the alternative hypothesis. The alternative hypothesis in this example is the claim. We have our significance level. Our significance level is alpha is equal to 0.05. Since we are finding the population mean, we use the sample mean and t-statistic. go to stat, t-stat, one sample with summary, because all my summary is right there. I know my sample mean is 6.8. Sample standard deviation is 1.99240984. And my sample size is 12. H0 is mu equals 7. And H1, sometimes called the alternative H sub A, but it's the same as H1. And here we have less than. Compute. Let's figure out what all this means. We're using the sample mean and t-statistic, which is also called the test statistic. That's right here. And there's my p-value. Use StatCrunch. We did that. And then we use the p-value to either reject or fail to reject. And what we're rejecting or failing to reject is our null hypothesis. Let's look at it on a straight line. Now, my p-value is my probability. First, is this a one-tailed test or a two-tailed test? Because of this less than, it's just a one-tailed test, where the probability or the area under this curve is 0.05. And then the rest is 1 minus 0.95. Now, my p-value is 0.3887, which is going to fall somewhere in the middle. All the area to the left is 0.5, and also to the right is 0.5. Half is to the right, half is to the left. And now my p-value, 0.3887, is really going to be somewhere around here, isn't it? It is not in my critical region. If it was in here, I can reject my null hypothesis. Everywhere else, I fail to reject. It's not that I accept, it's that I fail to reject. And I'll describe that in a minute. For this one, we're going to fail to reject. I'm always talking about my null hypothesis. We can't reject this, which means we just don't have enough data. If we fail to reject the null hypothesis, it does not mean that we accept it. And if we reject the null hypothesis, then we can go with the alternate hypothesis and the interpretation. Because we fail to reject the null hypothesis, we conclude that there is not sufficient evidence to support the claim that the mean amount of sleep is less than 7 hours. Since we can't reject the null hypothesis H0, we don't really know what to do. We don't actually have enough information. We're never proving the null hypothesis. We either can reject it and say, well, then it must be the alternative. We can fail to reject it, which means we actually don't have enough information. That's our only two choices. Just like if I was in court and I didn't have enough evidence to prove someone was guilty, I'm not saying they're innocent. I'm saying that they're not guilty because we don't have enough evidence to prove their guilt. Now, we can do the exact same test, but now this is with a confidence interval method. Our StatCrunch options. We have all the data here, but now we have a confidence interval. And the difference between a confidence interval and what we just had was the confidence interval is between two things. In here, either side of this would be reject. We have 90% confidence, 95% confidence, 99% confidence that our mean population is between here and here, that our mu is between there and there. If this is 0.05, then this also has to be 0.05. And now, instead of a 95%, which is what we would have thought we should have, we actually have a confidence interval of 90%. Compute. At our lower limit is 5.8. Our upper limit is 7.97. Our confidence interval is that mu is between 5.8 hours and 7.87 hours. 7 hours falls in there. Again, we can't reject the fact that it's equal to 7 because 7 is in our confidence interval. Either way, we actually get the same information. Is the mean body temperature really 98.6 degrees Fahrenheit? Measured body temperature with these statistics for 12 a.m. on day 2. First, are the requirements met? We can make the assumption that they're going to use a random sample. And also, n is greater than 30. We've met the requirements. Now we have to find the claim. What are we claiming? Use 0.05 significance level to test the common belief, which would be the claim that the population mean is 98.6. That's our claim. Now we have to find our null hypothesis and our alternative hypothesis. Our null hypothesis is always the equal, 98.6. Our alternative, it's not saying less than, it's not saying greater than, it's actually saying that it's not equal to 98.6. This is a two-tailed test. Significance level is alpha is equal to 0.05. If I was going to look at this on a graph, since it's a two-tailed test, half of this, alpha over 2, is in one side, which is 0.025. And also, the other half is in here, alpha over 2 is equal to 0.025. We've met the requirements, we found the claim, we found the null and alternative hypothesis, we stated the significance level. Since we are finding the population mean, we use the sample mean and t-statistic. We can't use the z-score because we're using samples. We have to use our t-statistic. We're going to go to stat, t-stat, one sample with summary. Our sample mean is 98.2. Our sample standard deviation is 0.62. Our sample size is 106. We are going to use a hypothesis test where mu is equal to 98.6 or not equal to 98.6. Compute. And look at my p-value. Is that p-value smaller than alpha over 2, 0.025? Well, it is. That means if I was going to look at my graph, this is 0.025. This number is way over in here, which is my rejection area. Now I can reject my null hypothesis. We can reject that mu is equal to 98.6. It is not. We can reject the null hypothesis, which means that the mean is not equal to 98.6. I did calculate this using our StatCrunch. Here is StatCrunch with our hypothesis test, and you can see that the p-value is very small. And here's the same exact thing with our confidence interval. And if you notice, 98.6 is not between my lower limit and my upper limit. All three approaches lead to the same conclusion. We're going to reject for the p-value because our p-value is less than the significance level. If we look at critical values, our test statistic is right here, and it's negative 6.64, which falls into the critical region bounded by plus or minus 1.983. It's outside of our critical value. If I were to draw a picture, our critical values are negative 1.98 and positive 1.98. And if we look at our t-stat, it's way down here, negative 6.6. It is in the rejection region. They all say the same thing. Confidence interval, the claim value of 98.6 does not fall within the confidence interval. How do we interpret it? We have H0 mu equals 98.6. H1 mu does not equal 98.6. We reject our null hypothesis. That means that we accept that mu is not equal to 98.6. There is sufficient evidence to warrant rejection of the common belief that the population mean is 98.6. Now I want to go through the phrasing of different conclusions. The concluding statement depends on which hypothesis supports the claim and whether or not we reject the null hypothesis. Remember, we saw two different things, one where the null hypothesis included the claim, one where the alternative hypothesis contained the claim. If the alternate hypothesis supports the claim and we reject the null hypothesis, the data supports the claim. If we fail to reject the null hypothesis, we have to say there is not enough data to support the claim. If the null hypothesis supports the claim and we reject the null hypothesis, we say there is enough data to justify rejection of the claim. If we fail to reject the null hypothesis, we say there is not enough data to justify rejection of the claim. If we fail to reject the null hypothesis, we did not prove it was true. We merely did not have enough evidence to reject it. We never accept the null hypothesis. Let's give a little analogy. In a trial, the defendant is assumed innocent until proven guilty. The null hypothesis, the defendant is innocent. The alternate hypothesis, the defendant is guilty. The prosecution must provide sufficient evidence to reject the null hypothesis. If this happens, the jury rejects the innocent assumption and returns a verdict of guilty. Otherwise, the jury does not reject the null hypothesis and returns a verdict of not guilty. The jury does not return a verdict of innocent. Similarly, in hypothesis tests, we never conclude that the null hypothesis is true. I think that this might help you understand exactly what we're doing in our hypothesis testing. Now we have two different types of errors. We have type 1 error. This is the error of rejecting the null hypothesis when it's true. We go through all of our calculations and we reject the null hypothesis, which means that we say there is enough evidence to prove the alternate hypothesis. However, we could make a mistake, or there can be a mistake. The probability of this type of error is alpha. In this context, alpha is a conditional probability. Then we have a type 2 error. This is the error of not rejecting the null hypothesis when in fact it is false. I should reject the null hypothesis and I should use the alternate hypothesis, but I don't. I say there's not enough evidence when there is. The probability of this type of error is denoted beta. The power of a hypothesis test is 1 minus beta. The power gives the probability of rejecting the null hypothesis when it is false. I think this chart will be very helpful. It's the way you decide whether you're choosing a Z and T. We start here. Do we know the population standard deviation? If we do, we go this way. Is the population normally distributed? If it is, we use our z-score. If it's not normally distributed, we find out if n is greater than 30. If it is, we can use our z-score. If it's not, then we use that alternative method that we're not going to talk about. Also, we could go the other way. We don't know the standard deviation of the population. We may only know the standard deviation of the sample. We go here. Is the population normally distributed? Yes. We use our t-distribution. If we say no, then we go this way. Is n greater than 30? If it is, we go back and use our t-distribution. If it's not, we use another method. I think this really will help you decide between a z and a t table.